Hello, this is the next topic. That's chapter 6 of our textbook by Zelsky. That's a feature-based alignment, but it's a little hard subject, so rather I call that pattern fitting. We fit the pattern. So there's a lot of fitting to do for this purpose. So let me go ahead and work on. This is chapter 6, so okay. Overview-wise, I would like to review that what we had that before. That is that so far to this so far in this semester, there has been several topics we have been covering in order, in steps. Then first chapter, we talked about the introduction to computer vision and tried to explain that how is it different from computer graphics and the image processing and then computer vision, then what is the purpose of it. But main idea is that we would like to understand the picture understanding or image understanding is a main purpose of the computer vision. So idea was this way, that you can make a lot of picture, and the human eye has and the brain has such a capability to look at the scene or look at the picture and get some idea right away. But machine can't do that. All it gets is a series of data, namely as a pixels. Pixel got when it is color, red, green, and blue. If it's a black and white, then it is just usually one byte of the different intensities. So some are dark, that's a 0 value, or very bright, that's depending on but 8-bit byte makes 255 as the value. So it gives the different intensity on each pixel, and then that grouped together give us some idea about the shape. So human beings can easily understand the picture and get some idea, but the machine can't. So we need some intelligent work for that. That's why I said the vision is a part of AI application. So in the second chapter, we talked about human vision versus machine vision. So human eyes, well, actually human eye itself doesn't see anything. It's our brain that takes care of all the seeing and understanding. So in machine case, that the camera is the one that capturing the scene or picture. But again, that picture itself needs to be processed by some brain, namely computer. So the main purpose, of course, of machine vision is that it is controlled by law of physics or optics, and the lens is low. So lens is more like a human eye. Something very distinct about the machine vision is that when you take a picture using camera that has in the lens, it is invariably that the monochrome, meaning mono view, that is just a single picture. Human eye has a stereo vision. Why? We got a twice. So modern computer vision is getting more of a three-dimensional stereo vision type of effect. So that is another mathematics, but primarily each picture is two-dimensional. So we got a two-dimensional picture combined together, and that compose in our brain as three-dimensional objects or the arrangements. Anyway, so we talked about how the machine or mechanical vision works. Then chapter 3 talked about the filtering. So we capture a scene or some picture obtained using camera, but then may be very complex or not very clean, noisy, meaning there are a lot of those errors or the some kind of undesirable part. So we need some cleaning it up. That's usually called the filtering. So filter means that whatever you don't need, then you just get rid of it, and you just get the essence of that. Just like maps, when they have there's so many scenes, but what you need when you are driving around the town, you need just the road and the main intersection and the landmark building or some location. So that kind of cleaning it up, cleaning our captured image. And then also when it is too dark, so not so good to distinguish it, or too light, so it is too bright, then we can change the intensity, and we can have some other effect of the making partially enhanced, so that overall contrast and information can be maximized. So that's the filtering. So it's a preparation. As a matter of fact, that up to the filtering, that there's no difference between the image processing, that IP up there, and computer vision. Then what is different is the next one. So chapter 4, it talks about, and we discussed, feature detection. So okay, we got a full set of picture in a page, or many pages. Then where do we start? We got to, in a way, detect or identify certain places where that makes a changes or some borderline. So here's a point. So we said that there's those connection or edge, those points, those the connection points, and or there's a line, so that's the edge we said. So where this area and this area is different for whatever property, and then what are those areas? So we talked about point as with 0 dimension, and the line as 1 dimension, and then area or the region as the two-dimensional entities. Actually, that's all we do, because as I said, the picture we captured by camera is always two-dimensional, so that's maximum we can go. Using that two-dimensional picture, compose it and manipulate it, and making 3-dimension is next step. Okay, so that's our feature detection, in a way that we checked on and generally marked up the important area. That's what it is. Then the previous lecture was about the segmentation. Segmentation means that we are grouping a certain area into one group, and another area another group. So here is one picture. There are a whole bunch of many things. Then we somehow separating out, and separating out that this is the one group, this is different group, this is the next third group, fourth group, like that. In doing so, of course, we need to identify that feature, that is the point, line, and the area. So that's what we had been doing so far. That's a quick review. So what is this subject that we are covering today? This topic is a pattern fitting. So we want to say, okay, there's the segments, and there's a few things that happen. So this outline, we got it, or maybe some color and texture inside there. Question is, what is this? What is this? Do you know that the name kangaroo, that's from the funny-looking animal from Australia? That one has very much have 4 legs, of course, but it is jumping with the 2 legs and has a baby on its pouch, and funny-looking. Anyway, it's a kangaroo. The name kangaroo came from the fact that when the Westerner came to landed in Australia, and they never saw those kind of funny looking animal, and the behavior is funny. So I asked those native person, what is that? What is that? Then he said, what? I said, kangaroo. So aha, so that's the name, the kangaroo. but turn out to be kangaroo means that, what did you say? That's the meaning. So anyway, what is that is important. So we identified those features, those points, lines, that is edges. When straight line, then we say that is typical the edge line, but it can be a curve, so we usually call edge. Then the area. Then area got into certain groups. So some areas, patches may be combined into one big chunk. And we say, okay, out of total picture, this much is one chunk, and that's one is another chunk, another one, like that one. So that definitely has a certain shape, So we want to identify what is this. Not only shape, it may have a color, it may have some kind of a pattern inside, some hatches or some different spots like that. So that they're trying to identify. So to do that, we must know. For those people who never saw the airplane, then when airplane flies, they don't know what it is. And even if they see it very clearly, they cannot identify it. That means in computer vision, to identify this thing as, say, a worm, or some animal, or insect, then the computer itself must have an idea or database, say that a worm looks like that in a different shape, and we got to fit that one into. So we need a whole bunch of those patterns, and we want to say, is the meeting that, this one fitting that, just of trying to find the best fit and say, okay, this is this subject is the best fitting. So we need library of or inventory of patterns that we want to fit into. So here is our picture or image we just captured. We would like to identify certain parts and want to know what this is a human, why it is animal, why it is a car, why it is an airplane. Then we need a pattern to match with. So that is what we are doing. So the different algorithms for the fitting patterns, and then search for the matching shapes. There's a different shapes. That's as a pattern. The pattern has a shape, and then I would like to fit. So there are many different methods. I'll give you the list of that, but least square estimation, or robust estimation, or random sample consensus. That is very popular. So this one will explain a bit, quite a bit, I mean. If you are interested, then read chapter 6 of Zelskis. It's a pretty popular and well-written book. So anyway, here is one picture of an old house or old hut, and then based on those coordinates, then we would like to have a shape. So there is one shape that we want to identify as a human. There's a certain shape that identifies an window as a window, and then this one they identified as a roof. That kind of a fitting into the pattern and identifying, that is our purpose, and of course it's a very important step in computer vision to understand the system. So let's explain what does that mean about the fitting. We had so far detected from previous the steps that we detected where are the edges, the corner, and the corners, that is points, and the general areas, and segmented. And we also did sift. Anybody remember what is a sift? You can dig your memory. This is very important, the technique. So for computer vision, the specialists, that you must remember this shift. So anybody says shift, I know what it is. That is a scale, invariant, scale invariant, and the feature, F is a feature, T transform. Actually, I should say transformation, but usually they say transform. What does that mean? That we say that here's the original picture, and there may be, I said, maybe a car, and it may be the tree, and the human like that. Well, there's a whole bunch of those components in here. So we want to identify this one as a car, this one as tree. It's hard to say that, and as a human. To do that, we need a pattern. So we talked about that we need a library of a pattern library, and there is like a car and a certain shape, and a tree, window, and a fish, and a person, and a plane, airplane, that is. Like that, there's a certain shape we can expect. So we need a library, and we want to fit or compare those shape to those pattern library, and say that this is a house, this is a person, this is car. We can do that match. To do that match or fitting right into the fitting, we need this library and the fit what at the time. But we did one way that we fit by pixel by pixel, but that takes too long and it doesn't work in many occasions, because that even if our the pattern library says this is a car, but actual places simplistically that it may be bigger, or it may be very small when it's far away, or it may be turned around, or it is rotated. So the shape maybe keep changing even if that it is the same objects, or it fits to that pattern. So what we need is we got to translate or change each of those library pictures or patterns, library of those patterns, into not a fixed form of the pixels that can be fit into, but rather we got to make some kind of a general characters. So anybody remember that what we talked about a lot in previous chapter when we are talking about the shift and also those feature, the detection? Something about eigen, remember that? Eigen value, eigen vector, like that one. So purpose of that is that, okay, this is our, say, pixel matrix of this car. But instead of just using that on and try to fit, that means this should be exact same size. So no, rather than that, we have this thing, but we will have, so this is a value matrix. Then we'll find a vector such a way that this times that is the same as that a value, single value called the lambda, whatever, and then this vector, this one is the same thing. So we put that on into so this one is the original shape or the object, the matrix. Then we call that one as A. Then we say A times V is the same as lambda times V. This V, same, meaning that we reduce this whole matrix into one vector and one value. There are more than one choices, but somehow it is very unique. So we call that one characteristic. That is eigen. Eigen, I said, is a German the word meaning unique, very specific to one and only, that kind of idea. So eigenvalue that we create, we derive or calculate So we tried with the 2 by 2 and not even try the 3 by 3. It's a very involved, but with the help of a computer, it can be done within hundreds of or thousands of a second. So it can calculate those eigenvector, eigenvalue easily. So what we have here in the library is those eigenvectors and eigenvalues. So with that, we have anything that changes slightly, then this value will change also. So that way, we have a unique one-to-one the matching between this original shape and this eigenvector. So using that, then in the object, we say that this one is whatever the size it is. Then we also reduce to the same sizes and create the eigenvectors and the eigenvalue and compare it and if they are matching or not. So that's the way that we can find the proper the objects to fit into. That's why the eigenvalue, eigenvector is so important. So once we got that one and we got this shift, the scale invariant transformation done, feature transformation done, what do we do next? So from a high level, more compact representation of feature by grouping multiple features into simple model, namely that is eigenvectors and eigenvalues. So that's an example. That's not the only way, but most popular way, and all the concepts or all the other techniques are centers around it. So anyway, so fitting is more like say that we want to make a fit, but much more flexible and widely usable. So that's the idea about that. So we have the objects here, then we have been detected the line that can be here, then there may be another line there, then maybe another line there. So we create many of different lines and you can make those connection. So with the feature that you can create those eigenvalue and the vectors, and that will be used for the actual pattern fitting. So fitting, what does that fitting mean? Fit. So I just borrowed some pictures from the Wikipedia. So here, this is a children's toy. There's a little small one, and a circular, and there's a clover leaf-like, and there's a half circle, things like that. Then there's a little pieces of this toy. So some toy fits to this. This toy doesn't get in through here. This one doesn't go in here. So there's a certain objects that fit into this certain shapes. So this original picture, and this fits here, this fits there. That kind of the idea that so you got a library of a whole bunch of those and just fitting into, or if you are working with some pipes, then there's this can be closed using this lead. But if size is different, you cannot close it up and the water will come out. So this one got perfect fit. No, we don't have to worry about it. You buy this piece all separate, and you just fit it. That way, perfect fit means that it is on the same match. That's what we are saying. Here's a pattern that is matching to this whole. Then this one is some kind of a bracket. This is a bracket, and there's two pieces of like a metal bar. And then because of that shape goes in, this one will fit perfectly. That's the advantage of those fitting. On the other hand, that we are talking mathematics and shape, so we got a few points, then it can be either fit to this long circle, the ellipse, or this shorter or the vertical, the ellipses. So with those several points, you can get more than one model So what's the best one? We'll see depending on other factors. Then here's a whole bunch of points we have the detected. So that is points we have detected at endpoints, whatever here. Remember that the Hough transformation is the one that either fit into the straight line or some kind of a circle using the points that you have obtained or detected. So that's the point. So we want to do the fitting. So there's a lot of fitting to do. Maybe this one is a little outside, but this is most modern. This is something I used to work on with the bioinformatics. That I don't know whether you heard about the word ligand. These days, that this COVID and the virus and the vaccine, that there's really the interest of everybody. So I thought that a little introduction of that may be good, interesting. So what happens is that when you got a real headache, then you take some kind of a painkiller, then the pain goes away. Of course, there are some cases it doesn't work, but that because the headache is different types from the medicine. So if you get the proper match, like a cough drops or like that one, then the main idea is that the drug itself is somehow working for your to cure your disease. So what happens is this way. We are talking about all organisms. So a virus or the bacteria, well, somehow living things. The bacteria, the virus is halfway between living things and unliving things. So in a way, each one has a unique shape. So ligand is the guy of little pieces of plug. So this is like a pattern. So they have a library of those ligands, and the right hand, there's a certain shape here. So this one, they look almost the same, but slightly different. This one is a little pointed, and this one is round on the back. So this is a perfect fit. So if you plug it in here, that means that that's why they put the color code. So if this little ligand is plugged in here, then this whole the original molecule is with this being plugged, it cannot move around that well. You need some kind of squeezing or some kind of a wriggling room, but it is all plugged up. So the drug, the medicine, is more like those little pieces of molecules, and this is can be bacteria or COVID virus. Then it plugs in here. So this one cannot function properly, and they got more like a bound. It's much like you are going around and do some kind of hitting or the jumping like that. But if your hand got tied, someone tie your hand, so your hand got tied and you cannot move around, then your mobility stopped and your function is stopping, isn't it? And suppose that I got completely the kind of plugged in with something like that, as I cannot move anybody, then I cannot function. So same kind of idea about that. So drugstore, the pharmaceutical industry, they are searching for starting for what is the shape of this empty space, and try to find the right size of a piece of a protein that will plug it in. So this is more complex looking the protein molecule, and then this is a bunch of ligand, not just 4, but there can be hundreds usually. So ligand number 1, number 2, 3, 4, like that one. And someplace, let me there, that this location is a little complicated, and that there's need to be some kind of changes. So that the green one is coming in and plugged in. So like that. So once this guy gets plugged in because of the shape of this molecule or ligand is fitting to the space available inside here, then it is just fitting, just like you have the stopper or some kind of plug. So plug stops in, and this whole protein can't function, so it becomes useless. So that kind of way that any disease, so you are not going to make your healthy cell be liganded, but rather the foreign attacker, the source of your the disease, like the bacteria or some worms, like that will be plugged in and cannot move. So that is a feeding. So same idea. Of course, computer vision technique being used often that to see if this empty space, or this is easier to say, this empty space is perfectly fitting to by this ligand or that ligand or that one or that one. So by those eigenvalue and the vector of those space and this value, this value, this value, this value, compared on, oh, this is closest, so plug it in. That kind of a way that you find the proper medication or drug to cure this disease. Okay, so that's a good thing about the feeding. So before feeding, as I said, we need a pattern, what to feed. So remember all those things. We are talking about the understanding the image. What is in the picture? So the maybe simplest one is prefixed primitive patterns. Then maybe so like a circle, square, and the color blue, red, and green, yellow, things like that. Or a little bit of those elephant and camel kind of pattern it may be. So they may be very simple primitive pattern. But what we need is that's rare to find any kind of the object that perfectly fit with the simple simple shape. Rather, that we need a certain generalized, tailor-made shape. So using specific shaping by curve and figures. So this is our picture, and we want to have suppose this is some kind of a toy soldier or some kind of some kind of the working actors in the movie. So what you do is that from this picture you create a pattern like that and a pattern like that by thinning and making invariant by eigenvectors, more like, or shift. So you have this. The next time that same figure is showing in the picture, you say, that's the picture we had before. Suppose that's that's called the robot X, RBX robot, like that. So yeah, we got that RBX. Then somehow you can model such a way these arms and head and the bodies in a certain way. Then even if that pose is slightly different, your hand is going up or down, and so slightly they're quite a bit different from this one, but the relative position and arms are there, then you will be able to identify it as the same the objects. So you have a perfect fit, or the close or the good fit, like that. So pattern primitives, so square, circle, rectangle, blah blah. Then there it can be different colors, so like that one. So using various color, actually you have a shape data and the color data and the pattern data. Then you can make many the combinations of that as primitive. But complex pattern need to be generated. So it is more like the tedious work, but my computer can handle all those things. So from existing data, even human face, that it generates the kind of pattern library, and using that, there is strength to the match. Actually, one of the technique about face recognition is that everybody has the eyebrows and the eyes, nose and the mouth like that. So you have a database for the this eye part and the nose part and mouth, upper lip, lower lip part, and using that as the fitting. And again, if you have those things are sifted, SIFT, sifted, then it can be applied to different sizes, different orientation in any way you like. So build a pattern library for matching based on base image data, or from design based on our imagination or our experience, like that. So you have a complex pattern generated. So one method is that this is the picture in the book, that the 4.23. That is that this picture, many these pictures. So you have an edge detection and clean it up and come up with this kind of a simple important the skeleton of the shape. And here's some shapes, and you have shapes like that. So even if it's very complex, you can make it much simpler, and it is useful for the library. So very often that like this scene, a little harder to see for you, but it's just a scene, very much like you go to Terology and take a picture. So if you want to know that if this picture matches with Terology National Park, then you can get this general pattern here. Oops. This general pattern, and then you can get the matching done in the different areas. So as I said, the starting point is our picture contains a certain region, segment, that is. Segment has a certain shapes, and that shape has this one, and then this is shape. So two segments being combined together for matching with this picture. And again, using those the scale invariance and this unique vector, eigenvector, that you can they make a more general form of matching or comparison. It doesn't have to be exactly perfect match, but the character matches together. So in doing so, the general curve can be traced here from here, first location to this way, and that location. So that path brings into shape data, and then there's a motion data. Even it can be changing from one step to other. So various changes can be kind of recorded and used as a big matrix like that. And using the matrix again, you have a characteristics of a V here. Compare it. So you can get much quick and versatile or generally applicable pattern matching you can generate. And then again, that in this case, that the different shapes, so from the based on the line and the circle and this area general shape here, you can match this guy with that. So in a way, the matching goes that we try to fit this much, or partially matching this much, then this is perfect fit. So overall, percentage-wise, how much fit do we get? How successful was it? That the fitting we can expect. So we need some parametric model rather than actual data one at a time. And then it says membership criteria is not local, meaning that you study the fitting. You have this shape, and this is our pattern. So suppose it is matched only this much. That's locally this fit, but maybe not enough. So you have to look total picture to everything together, and how much does it match. So a point belongs to a given model just by looking at that point, but we need say that how they are fitting well. So they represent this set of feature best. So again, remember those feature we talked about in previous chapter. So important. There's just a point, line, and area. So here makes us a shape. That including segments. But so do they fit best? Because here's a certain shape that we want to identify, but there's so many pattern library candidates. So it may fit with this, fit with that, try with that, try with that, all kind of the different possibilities. So which one fits best? So you got a choice. So sometimes later we may be able to talk about it, but a shape of this one, then like a cat and the dog, they look so similar. There are so many components. So for the machine, that identifying as cat or dog isn't that easy. Human beings is easy. So that kind of the process of identifying it as a cat, identifying it as a dog, that depends on that what kind of a feature we are dealing with, and then how many model instances are there. So in other words, that this one, all those model pattern, the library, that each item, we call that one as a model. So fit that model into our target for the matching. And the computational complexity is important, meaning that this is sometimes very time consuming because the picture gets very complicated. Then there are so much of parts within a picture, and that picture, the parts, we got to consider everything together. So that takes too long, very often. But so we need an algorithm that's that takes less time to do the calculation. That's the kind of our goal of having good fitting. So here also that even if we already have cleaned something, this is a funny looking car, but this this is a model that we want to fit. Then there's some kind of a noise. Noise is not only just kind of little dark noises like that one, but this color is the same. This color is the same, so that confuses. This line may be confusing with these lines. So they are kind of confusing other factors. This car is not just isolated, but it's the part of another scene, and that other background may be confusing our identification. So we have the itself has some kind of different kind of noises, so-called, and then they may be the extra data. So these lines and other lines are making it more confused. Which one is front? Which one is back? That's not easy. So when you see those graphics, the library, the graphics software that removing the background, when it's complex, it takes more work. But anyway, the removing background is pretty hard job. So but all those techniques are already well established. So all you have to do is just to use it. And then maybe some the missing data. Missing data here in this situation means that it's occluded. Occlusion is hidden. So some part is hidden, or the other side. So we don't know what they look like on the other side in here. When we are looking from this end, what do they look like? If there is a window, are there window wipers? Then top, how do they look like? Or let me go with a different color. Then how's on the other side? So those a part of a picture that is there but not captured because of camera angle, or sometimes there may be somebody standing in front of a car, so they are partially hidden. The light just goes straight, so once there's any kind of obstacle, then it doesn't show. This part cannot be seen. So that kind of the difficulties that exist in fitting. So there are many algorithms. So first one is a brute force. So what you do is that exhaustive matching by pixel by pixel by pixel. In 2 weeks ago, we did this the template matching by the counting number of fits, like that. I don't remember, but that's a brute force. For simple small scale pictures, that sometimes the brute force works fine. Because the computer is fast, but it is not very elegant, and it is not that easy to do, and also that there's a problem with the scale changes, so we cannot do with the scale invariance. Then this with the shifted images, we can do convolution and matching it up, so that iteratively matching and construct the hidden line. Like I remember that there's a relaxation method that actually, even if that there's a line is stopping here and the next line here and there's a missing part, it is just going through, seeking it out and hit the matches, that kind of thing. And another one is a least square method. That's calculation that there's a whole bunch of dots, and you have a linear or some curved line or some shape, and how far away they each point to those idealistic the equation, and then they find the smallest, the kind of a model that is the error is the smallest, like that. Then maximum likelihood, this one is a minimum error. So you take first derivatives of those error function, and when they are zero, that means it's a Plato minimum first derivative. Of course, it can be a maximum location, but the typical quadratic equation has only one the peak, and usually we know that when it hits the peak, that's minimum points, so that we can get that. So that's a minimum error part, maximum likelihood method, MLE it is called. So frequently used in the statistics, and using that one for genetics and some other application. Then RANSAC, this is something new that you haven't heard about. So it's a random sample, the consensus. Actually, this A must be capital letter. I did it, but somehow we went back. So random sample consensus. So you sample randomly and see which one fits best. So this is pretty the popular and well done and the algorithm, and used a lot with many variations. Then success was deep learning, okay, DL. So these days most popular one, the Keras, you may have heard that the Keras, that is more of a host language. And the library, just like OpenCV, there's a TensorFlow, Theano, and the Play, the ML, like that. Those things are very popular. The computer vision oriented, the deep learning, the utility. So hopefully we can talk about this deep learning part, but I don't know how much we can. Okay, so we want to find the most optimal the parameters, and so we need if we know which point belongs to which line, then we need the best way we find the optimal line. So suppose that these points, we have this one. So suppose that these points are all coming from the line. Remember those in relaxation? Then there's a line like that. So gap here. Then by having some kind of a linear function going up to here and another one, and then you can fit in 2. So that is done by least square methods. Again, that this is all statistics, so I know that is going to be hard, but let me explain it at least to a certain level. Then, of course, that the outliers and too many lines, and we don't know, there are so many lines, we don't know what to do. Then least square is not good. This is a simple case, and then the random sample, the consensus is the more useful. So you go to this location. When I click this one, then it doesn't show in the video, so I'm just sticking to. Why don't you just click this one? Or there's if you go to the Wikipedia, then they have a very good explanation of what is a RANSAC method. So just to say, you got to from Wikipedia, either random sample consensus as a keyword or RANSAC, and see what happens. I think it's both works. So it is very useful, but this is the British, the author Fisher, who's pioneered on RANSAC method, and this is a very good introductory article. So if you can read it, that's great. If not, still, that whatever we cover here, then may be enough. And then even if it is a line, you're not sure even then it's a line or dot or it is a circle, what is a part of it or not. Maybe then you got to choose different selection of the model and the patterns, and it can work. So what kind of method to use for each case? That's what it's talking about. And if too complex and it doesn't seem to be working, then go to deep learning approaches of having a huge database and feeding into using neural networks. Okay. So let me explain just briefly about the least square line fitting. But before I go on, you can take a break and come back if you want. So this page, but for the lecture, I'll continue on. Okay, so least square method is that the smallest square. So something squared, and you sum it up and to find the minimum M and B. So what it is that you have a dots. This is very, in a way, the elementary but also very essential part of statistics. So you have observed these points, this point, and this point. So we have these points, and what would be the line, linear straight line, that will fit best? So fitting best. So statistics in maybe in about the 8th week that they usually cover this least square methods. So idea is that okay, we don't know what it is, so this is yx plus b. So in here we got an x value, don't we? Then we don't know what it is, so we want to solve for y, and I'm sorry, we want to find what is m and what is b that makes the best fit. So in other words, suppose I got a dot. Then this may be best fit. This may be the best fit. This may be best fit. We don't know. You got some feeling about it, but number-wise we don't know. So best way is that okay, this is the one. So that one is y equals m1 x plus b1. M2, 1, like that. So whatever the value it may be, so find those. Of course, we don't know, we're gonna do randomly. But anyway, so idea is that this distance, so if this is best, I mean, the best case is that if everything is perfectly aligned, so you draw it, everything's on the line, then the value will be those difference will be 0. But what happens is that here, that in this case, that this is we have an x value, this one is x and the y value, this is x and y value, like that one. So this is what we are expecting. So this value is that actually this value mx1 plus b, that is the value of when this one is right in here, isn't it the case? Because of the x, this is our x value. X value is here. So when x is, say, 2 and this one is 3, suppose this is 2, 3. It doesn't look like it. 3, 2, 2, 2. Let's do that. So when x equals to 3, then y is 2. But this, according to this line, then we don't know y is mx plus b here. So the value, the point value here will be m. We don't know. We suppose we know m times b. So m times 3 plus b. So of course we are deriving this one by first derivatives. So, but we are off. So how far off? So we take away. So yi minus this one is mxi plus b. So those differences, these height differences, we square it. Then this one is when x value become say 5 and whatever 5 and 7 like that. So we want to say that according to this, that's going to be a 5m plus b. Of course, the 5 there we're going to calculate the m and the b later. So this value, so that's what we are expecting, that when the point is right on the line. But if it isn't, then we know that this is 5. So suppose this one to be exactly here, this is 5 and 6. But turn out to be 5, 7. So the difference is 7 and 6. Suppose this one is 3, 2, and this one's supposed to be 3 and 5. Then 5 minus the same x, but y is that 5 is the right number. But unfortunately, our value is 2. I mean, the 3. Suppose 2. Then the difference is 3. So we square the 3. So 9. And this one, difference is 1, then 1 squared. And about this one, there's suppose 2 difference, then we square, so 4. So all those difference from theoretical value to actual value being added, squared, and added the y squared, because that when it is minus, there's a plus, there's going to be different. So you derive x and y by just the line equation very easily, but eventually that this one minimizes. So I point, there are n points in here, so sum up those differences of squares of differences, and we want to make that on small list. So if what we do is that with those, then we got those m and b and x1, y1, all those things calculation. So you can calculate m and x, m and b by this inverting the matrix, because you got so many points. So you will do it. Looks like calculating eigenvalue and eigenvector, but actually it's different. So m and b, that's the difference. So you calculate m and b based on minimum of those these differences. So find the m and the b such a way that this whole quantity is summed up is minimum. That's the idea. So you take the first derivatives for that. That's what you do. Okay. So normal equation is a least square solution to the yb equals xb equals y. So you calculate the b value, and there's a problem with the vertical least square. That is that when it's a rotation, then there's going to be quite a bit changes. It's not invariant. Then when it is a vertical line, there's no way you can fit that one, because not everything is on. Every y value is exactly the same, so there's no differences, no square value. Every square value will be 0, so it doesn't work. It's just terrible. So rather, total the least square method is that they're using first the the calculating and the first derivatives and the partial derivatives of those expectation with the d value. That's three the constants or the scalar value, and you solve that one, and you eventually come up with the solution of A, B, D, and that's giving you the solution. So the least square method is a statistical method of what would be best fitting. I think I told you before that it's much like the inner town. It is these are the gales, so it's a pretty wide big area, the wide area, and the one house, one gale here, another gale, many gales in here. They want to run a bus line. So what would the bus line going to be? If the bus line goes straight line, they go this way or that way or that way, like that one. Then the best way is that let the distance from the their house to this bus line is a minimum. Then people will be happier in a sense. So that's the same idea about the least square. So this solution is and eventually then going with the eigenvalues, eigenvectors. So using those eigenvalue, eigenvector, that you can get the solution to the least square methods. So the total least square method is much like a principal components, and then you got to do dots, and you know that which way is the vector and the distance from center to any straight line, and then those whole calculation, the centers around finding the parameters, that is m and b, such a way the distance squared from each point to the line is minimal. Then least square is the likelihood of the maximization. So there's a likelihood function. You create the function that is the most likely. So I'm not going to talk about that, but the generative model goes that the line goes in here, and you get the minimum, not only minimum, but the vector-wise, the shortest distance rather than y values, the shortest distance. And so the principle is very similar to the least square, but likelihood maximization is more flexible and known to be better working method. But I'm skipping that, so because it's complex. So you have an expectation and the minimum of this expectation value and exponential. This is more of a Gaussian the distribution, everything based on normal distribution, and then assuming that which one is most in the center. So the based on normal distribution. Linear square or least square method didn't talk about, or then it doesn't consider any Gaussian distribution. This one does, and that works better. Again, this is a little complex, the statistics, so I'll just pass it. Then the general curve wise that you got to when these dots are more of a circular, so instead of a line, if it is a circle or ellipse, then we got to have a model that fits best. And the conics, that is conics is that that's a cone. You see those kind of shapes, and the conics is that you cut here, and the shape will be this ellipse, and straight like that, and there will be a perfect circle. But so if you hear the same exact circle, but it is smaller, this one here, then maybe bigger circle, and then you go like that, then they get the halfway of the cutting. Always go through that minimum, then will be very oblong method. So you can get the least square for conic shapes. That equation is more like that. So there are many parameters, so you can they get more complex calculation, and you got to use the matrix. Just giving you the idea that this computer vision, the process uses a lot of mathematics, a lot of statistics, a lot of calculus, and a lot of this the AI logic on deep learning. So there are many the least square for the conics. So any kind of shape can be estimated. And then robust estimation means that you just say no shape. It's much like a non-parametric equation. That means it does not assume any the model. It just to say, okay, get me the fit, then I'll give any kind of a function, but in more of a polar coordinate system. That way, it can be any kind of shape like that or like that. You can express the best way. So this has been done. So the computer vision borrows a lot of those techniques or the theories already developed in statistics a lot. So this with respect to the model of angle theta, so this conic sections and the changes. And this is nonlinear optimization, and the general one. Often that magic number times the median residual is adaptive choice of scale. So this one is more about the heuristics. So when you are calculating how much standard deviation or how much distances we should expect, so I usually say 1.5 as a kind of a value into median. Then may give good estimates. That's the idea. Let's go to the idea about the RANSAC, because we don't have much time. So robust fitting deal with a few outliers. So if there's a few things that's way outside, that's the outlier, then whole calculation mess up. So how can we solve that problem? In the case that random sample consensus, so what they do is that you are sampling from the whole picture, you are sampling the random number from everywhere, and then try to fit how many of them are fitting best. So they choose a small subset of uniformity at the random, this chunk, this chunk, this chunk, this chunk. Sounds like when you got a picture from the Mars or the Venus, and there's so many data there, then you are just checking into the sample here, there, and see which one fits best. Sounds it is a very obvious approach, but nevertheless it is working very good. So in fact that this has been studied in a long time ago in 81 that by the Fisher and the Bowles, and they are the cartographer, they are map making person. So they had some picture from the aerial photography, and try to fit from existing data or in the map data, and which one fits best. So this one was done for the military purposes or geographic purposes, so survey-wise. Then when you do randomly sampling it and start working on, it worked pretty good. So that's why people started using it. So in here, a few things that are used as a LDP, that is a location determination problem. So the Fisher and the Bowles, they say, here we have a partial map. Like you go to the Google map and a certain area, I don't know where it is. Then you will start checking with the overall picture with the random samples. Then they construct the 3D pose based on 3 points. So sometimes, if it's possible, then map is available. P3P, the problem is that the perspective of 3-point problem. So you can kind of get reconstruct three-dimensional data from existing data and check which one is fitting best. And the direct linear transform, the process of constructing 3D points by linear transformation. So these two things go hands in hands. So when you are matching a point in a map, then it can be more accurate. The fitting is more accurate when it goes to three-dimensional the level. So LDP, the dimension in here. So the center of perspective and how far it goes. Let me change the color. So you have to see these small pieces of the land. So you got those random sample here and triangular sample here, triangular sample here, triangular sample here. Then you are checking, and then find what is the most the best fitting location. Somehow this works pretty good. Then there's a P3P, the point 3-point perspective, 3-point problem can be easily, they're pretty well solved by that. So when you are, this is the algorithm. Again, that I don't know whether I should explain it or not, but what it is, you keep doing it, and the good thing about it is that you continuous doing sampling, and fit until the error you are calculating from this fit and the perfect fit is close enough. So that you would say, oh, this is good enough fit, and then you are stopping. That's the idea about this one. So you do iteratively, keep doing this one many times. So it is select randomly minimum number of points required, then solve for the parameter of the model. So from collected data in that sample, then you calculate A, B, C, D, depending on this the circle, or it is a line, or it is the ellipsis or conic. But or that you originally they did it as a landmark that this one fits, that fits. So certain the specific data fitting, that is what they worked on. But anyway, so you keep working on how many points from all points fit to the predefined tolerance. So you just keep running. Older days, this took quite a bit of time, but nowadays the computer is so fast, and they can handle it with a large main memory. So this one, a random sample, then you can get pretty satisfactory. It's in a way that I said brute force. That is that you check every possibility. So when picture is complex, then checking every possibility is impossible. But random sample is next best one, and in general it works pretty good. So this is the way. So fraction of a number of inliner, I mean, so within this range, and then you fit this one. So suppose that out inside here, there's many features, and here's another many features. So the original map here, this one taken out, and this one has a certain feature, and this is our the template. So we sit here. So out of there's a features of dots, corners, and here. So in other words, that suppose that this one is the aerial photography of Hure, the university there, and there's there are 3 buildings, and there's some outside the wall, and or something. So those things are few features. So with that, there's a total 28 features to look for, and the area that had somehow matches only 2, no good. Then another place, then matches, you sample this one, only 5 matches. Here, well, 17 matches, that's good enough. Then another place is about 6, no good. Then it's about 20, like that one. So one place you finally found it, and 22, and no more. Then you say, oh, 22 matches out of 28 is like the 80%. So that's good enough. So you just keep doing this one and say, oh, I found the A location that fits this feature comparison with 80% or higher matches. Then I say, okay, that's good enough. And then you just conclude that this is all. So you find the location of a matching. So this is more of a detailed algorithms. There are a lot of software that's already implemented this one, so you don't have to worry about too much. OpenCV also has this one. RANSEC also. So the choosing parameter isn't that easy, but anyhow, that total number of points, that's a minimum number needed to fit the model. So you can make a determination, say that I got to at least that 5 is a minimum, like that one. And the distance threshold is that no more than the 35% or no more than 20%, things like that. You can decide that, and how many samples you can do. So you can easily go to 100, and it works pretty good. So there's a Python programming that actually does this one. So take a look at it. All you have to do is say, what kind of OpenCV that ran, SAG, how they are working. They work just fine. So there's a few pros. The simple and general, applicable to many different problems, and that works well in practice. But lots of the parameters sometimes, and always good initialization. Sometimes it may be much like the brute force. So sometimes it takes too long, and sometimes too many iterations are required, and can fail extremely low inline ratio. And inline means that it is fitting inside, and often do better than brute force sampling. So brute force, as I said, the RANSEC is much like brute force, trying everything, but it is working better. So I would say, yeah, this is a good choice. Then other choices, there are other issues in the matching is that if it is a three-dimensional alignment, then there's always issues to look at it 3D. So you got to reconstruct 3D model, and your model or your template must be 3D also, and must have the comparison to do for 3D, and matching and panoramic the scene composition is needed for you usually have multiple pictures, and how would you fit those things together to make those connection. And then there is an issue about the pose estimation. In other words, that certain moving objects like a car, human, animal, they are changing. So same person or same object, but the change the position, then in the case, how would you detect that? Again, that is what I said. That you have a car as a kind of your template, and you want to detect how many cars there is, but the car may be they going back, they just straight on, or what we have a thing on the top view, so we have no idea. So it depends on the situation. So in the case of any way they can be estimated, yes, actually section 2 of the chapter 7 talks about this one about it. And then the calibration of a measurement and the instrument is also another big task we must have. And feature-based alignment in here is the proper matching issues in here, and sometimes we worry about how things will work when things are in motion. There's something changing. So again, that motion issues is the chapter 8, I think. Okay, that's all for today's lesson on this feeding. It's a very difficult subject, and I feel like it takes a very long time to grasp the concept, but hopefully that you get some ideas. So as a summary, that after detecting features, that is point, corner points, and the edges, and the region area, then do the segmentation. So we separate out certain group of pixels as one unit, another unit, like that. So multiple units. Then must fit to the pattern to understand the image. So this is the fitting is a very important stage in the fitting or the computer vision, that is understanding the image. So many techniques. So as we can see that human eyes and the brain has evolved so long years to make those recognition instantaneous. So same thing, the machine must do a lot of hard work to understand the image. So as a first step, fitting. This one fits to that, that fits to that. So it's brute force methods there, and the least square methods, and the maximum likelihood method, and the RANSAC, and the deep learning. Just remember that RANSAC, that is a random sample consensus. Okay, the rest of this subject that we're gonna cover is that first of all, there will be optical flow. That is based on chapter 7 and 8. Then very important one, that is the recognition. Actually, this recognition alone takes, I would say, several, maybe a whole semester for make it better. But now that we'll do just to simplify it. So chapter 14 will be recognition. Then whatever time we have, we will talk about the face recognition. That's a similar idea. But the face recognition is somehow different. So this is from other sources, and here we'll talk about the DL, the deep learning aspect of this recognition, while talking about the face recognition. Okay, so that's all, and thanks for listening, and we'll see you next week, and have a nice weekend, and have a nice days. Bye.